Right, so the next paper we have presented is context-based style transfer of tokenized gestures. The authors are Shigeru Kuriyama, Tomohiko Mukai, Takafumi Takatomi, Tomoyuki Makasa.
Moderna, you probably stop the sharing. Okay.
Could the next speaker come here to?
Okay. Okay. Can you hear? Can you see this right?
Yeah. We need
to stop the sharing here.
It stopped.
Okay. Can I start now?
Hold on a second.
Yeah, okay, sure.
Yeah, so they can start sharing.
Okay. Sorry.
Yeah.
And double click it.
Sorry, is it working?
Yes, give us 1 second.
Moderna, you double click it.
Okay.
Yeah.
Okay, yeah, please start presenting. Thank you. You can go ahead and start the presentation. Can you hear me?
Yes.
You
I'm
start?
ready.
Yeah,
I'm totally ready. Oh, yeah. Okay. So thank you for the introduction. My name is Shigeru Kuriyama. The title of my talk is a context-based style transfer or tokenized gestures. Can you hear me all? Okay.
Yes.
Okay. Yeah. So our research aims to efficiently and flexibly transfer the style of characteristic gestures. And automatic gesture sentences from voice or text are now hot topics, but many of them cannot flexibly control the style of movements. This movie shows one use case of communication in a virtual world. It is essential to transfer the gesture style to match the avatar's appearance, in this case, like a robot. However, the big problem is the limited availability of datasets for such characteristic gestures. Therefore, our transfer should be implementable, even for a small dataset, and requires no tedious task for clipping and labeling. Additionally, it should be computationally efficient for real-time interactive systems. I first explained the difficulty of our gesture style transfer. This plot shows the time variations of latent variables for various working. Clearly, every movement has high correlation over time. Therefore, we can transfer features by globally changing the offset and scales. However, the latent variables of our gesture motions have little correlation between the content and style colored blue and red in this plot. Here, the purple lines correspond to imaginary gesture after style transfer. Interestingly, this ground truth imitation is partly not correlated. This plot also shows the difficulty in treating gestures. We can see that every working style can be successfully separated on the left plot. On the other hand, gesture styles from our dataset could not be separated by the same encoder. This is because the features of gestures emerge within a local period in various styles. Unfortunately, this suggests the existing method requires the troublesome task of manual clipping and labeling. And we actually could not transfer the style for our dataset using this generative model. We tackle such a difficulty by introducing a patch-based approach in image style transfers. The key technologies of this method is the swapping of block-wise latent variables called patches between the content of natural images and drawing style of paintings. The swapped patches are selected by pattern matching based on cosine distances for style swap on figure C, or combined with whitening coloring transformation for style decorator on figure D. These approaches try to rearrange the patches of style images so that the resulting image have a similar structure to the content. We think this patch-based conversion is helpful for the motion pairs of little correlations. The other relevant method is the semantic appearance transfer using the vision transformer. A block of pixels is considered as a visual token, and the transformer processes this sequence of these tokens. This method successfully introduced the loss functions for structure and appearance using the variables inside the transformer. We similarly introduced the loss function for preserving the content and style features. However, as this method requires the generator for synthesizing the output, we instead introduce the decoder of transformer and token-wise swap introduced in the previous slide. This shows the architecture of our system in synthesis mode. We first embed the upper body motion with a convolutional autoencoder for content and style gestures. Next, the latent variables are divided along frames to compose tokens, then used as input to our style transformer. Finally, after swapping the tokens between these two types in the transformer, they are concatenated for restoring the upper and lower body motions through each decoder. Please notice that the encoder reduces the time resolution of 60 frames per second into a quarter. And our pose vectors are composed by only joint rotations represented by a logarithmic map. These figures show the architecture inside the style transformer. The encoder and the decoder are the same architecture as the vision transformer. And additionally, we introduced the swapping and blending mechanism of style tokens, as shown in figure C. This soft swapper allows various styles to be managed without retraining, which means unsupervised and zero-shot running. This schematically shows our loss functions. Similar to existing methods, we introduced two types of reconstruction errors. One is for identically transferred motion using the same sample for content and style. And the other is for cyclically transferred one, where the output of style transfer is back transferred with the content. In addition, we introduced two more loss functions for evaluating structure and appearance. For the content components, the loss is computed by the self-similarity of key variables used in the transformer. And for the style component, the learnable parameters of the transformer, called class tokens, are used to compute the difference in appearance features. Then our loss function is given by the total of these loss components. This shows the dataset we used for training and evaluation. For training, we used 7 ordinary gestures as content and 9 style gestures, including extroversion and anime-like styles. For evaluation, we collected 15 gestures whose styles are freely performed according to each talk scenario. And we asked a professional female actor to perform ordinary and expressive style for each scenario. We also asked the actor to imitate a good transfer example, which is used as a ground truth case. This movie shows the transferred results from the start samples of a different scenario. Okay, so here we introduce two types of error metrics for quantitative evaluations. The content error is measured by the distance of time-warped hand positions because the spatial trajectory of the hand often implicitly represents the meaning of messages. On the other hand, we quantify the style error by the means and the standard deviations of hand velocities because the distribution of the speed are often used as style features. However, these style features suddenly and randomly emerge as local events. Therefore, we compute the minimum differences of these statistics within each 2 seconds. This chart represents the comparative result of errors against the imitated ground truth. Here, owing corresponds to the aberration of token-based composition, and the alternate is regarded as the aberration of the transformer. And the hard swap means that we swap tokens by simply replacing them instead of blending them with softmax weights. These results show that our method has the minimum error for all metrics, except that the worst content error is slightly smaller in the other in. Interestingly, our thought swap can largely reduce style errors compared with hard swap. These are computed using the content and style pairs with the same scenario. And we obtain similar results for the pairs of different scenarios. The errors are slightly increased for this condition, but in most cases, the order of magnitude was invariant. This demonstrates the qualitative evaluation of the aberration studies. The style gesture is sampled from a different scenario. We can confirm the incorrect pose of the existing method from the viewpoint of content preservation. In addition, unnatural vibrations emerges at the hard swap as shown here. Okay, this example demonstrates that our method can handle style samples performed freely without using any talk scenario. This shows that our transformer could interpret the contextual structures even from such chaotic behavior. This shows the effect of token size. In image style transfer, smaller patches increase the content similarity, and larger patches increase style similarity. And for gestures, we can also control the trade-off for these similarities by changing the size of tokens, as shown here. However, we found that the effect is not so consistent compared with the image style transfers. Our methods still have similar limitations. Firstly, it cannot transfer lower body motions meaningfully, and the lack of controllability often causes kinematic errors, such as foot sliding. This defect is common among the existing methods because the style of upper body motion is not directly reflected. That means the lower body motions are often driven as a secondary motion of the upper body. Secondly, the diversity of our swap-based transfer is largely affected by the variation of style motions. For example, suppose the style sample does not include similar structure to the content. In that case, the resulting gestures cannot follow the content or generate unnatural motions due to the blending of many unrelated tokens. Finally, we don't have a reliable metric for balancing the preservation of content and style. The best trade-off actually depends on the scenarios or situations. So we need intuitive and interactive tools for adjusting the balance. Now, conclusions. I have proposed unsupervised zero-shot learning for gestural transfer. Using this context-aware transfer, we can match up style tokens with content, not at the signal level, but at the semantic level. Through this flexible correspondence, we can robustly transform complicated gestures. The on-the-fly transfer should be developed for implementing interactive system using some contextual autoregressive models. And for the scalability, we need to compress style samples while optimizing its essential context. This is all my presentation. Thanks for your kind attention. Thank you.
Yeah. So do you have any questions?
I have a
Sorry,
question.
I cannot hear. Okay.
You can hear me?
Yeah.
So I have a question. Could you give a bit more intuition behind the error metric you used for measuring the style, using the mean and standard deviation and that stuff?
Yes. Ideally, we should compare the all the pattern of the variation and change of the velocity, because I believe that the timing and the speed reflects the the expressive feature of the gesture. So if we could very good metric, we should compare these complicated pattern. But now we don't have such useful features. So instead we replace these features by the standard statistics variables or the velocities. Yeah.
Yeah. Okay. That makes sense.
Yeah, so just a quick question. Does your method have any knowledge of gesture phase, like hold or retract? Do you take into account the phase of the gesture at all?
Sorry, it's very hard to hear. So are you asking about the phase of the gesture?
Phase of gesture, yeah. Does it take into account gesture phase?
Sorry, I couldn't catch your voice because the trouble with the sound. So
Does your method take gesture phase into account?
gesture phase? Are you asking about the phase of the gesture, right?
Yeah.
Yes.
Okay, so our method cannot handle the phase information because we simply pattern matching as the using the per token. I mean that some 60 frames are together compared with by neglecting the such phase information. So, but I think that it is very difficult to define the phase information or extract the phase information, like the walking styles. For example, this figure deep phase was successfully introduced, but I think that introducing such, the extractor for phase information maybe failed because our expressive gesture is a very complicated, phase information. But I will try to, yes, I would like to try to introduce such, the phase extractor proposed in the figure, last figure. Yeah.
As to the synchrony with speech. Do you lose the synchrony of the gestures with the speech if you don't take into account phase?
Sorry, the sound is very hard to comprehend. So please interpret.
With speech?
Please, Chairman, please interpret.
Yes. So this microphone you can hear okay, I guess. Have you tried it with speech, and does the timing of the gestures change such that the speech doesn't fit anymore? I think that's the question.
I didn't try it because our old data set is captured by the synchronizing the spoken speech. I previously recorded the speech scenario and the performer do gesture according to the speech voice. So we don't have such trial.
All right, thank you very much. So let's thank the speaker one more time.
Thank you.